Sorry about that. The key to identifying those sites is looking for the double bond. So wherever the double bond is, it's always going to be the carbon right next door. So in this case, it'll be this one and this one. Because that's that by definition, allylic means adjacent to an alkene.
Okay. Okay. I got it.
Yeah, so that's how you identify them. And then once you identify them, then you'll know for the allylic bromination, you'll know where to take your hydrogens from and where bromine is going to end up. Like even if you don't go through the whole mechanism, you know at the end of the reaction, you're going to have a product that has bromine here.
At the bottom.
Then you're going to have another product that has bromine.
Okay.
There, right? Even if you don't go through all the arrow pushing.
Okay. Thank you.
Yeah, you're welcome. All right. Any other questions before we go back to alcohols, alkyl halides, and all that good stuff? Okay, so let's jump back in. I think the only reaction we didn't do was thionyl chloride. And let me change my pen. It's too thick. So we start out with alcohol. So this is thionyl chloride is this molecule right here, which is shown over here. All right, that's thionyl chloride. The thionyl part is the sulfur, oxygen double bond. Like it's like an analog of a carbonyl, right? So a lot of times when you have sulfur containing compounds, that you call them thiol compounds. So this is a thiol. Sorry, my fingers. I just finished working out, so my fingers jacked up. Thiol for sulfur and nil for the carbonyl similarity, like a C double bond, no, it's an S double bond. But anyway, so we have thionyl chloride. This method, as you can probably tell, is specific for primary. It works on secondary. It's a little slower on secondary, but it's specific for primary alcohols. So when you see primary, it's like one degree, that means primary. So primary, and then ROH is just an abbreviation for alcohol. All right. So the first step, what's happening in that first step? Anybody?
Convert OH to a better leaving group.
Well, yes, that's part of it. But if you look at what we did to the OH, what happened to it over here? Is it still OH?
No.
Yeah, this is.
So we had to, it was a deproton, I mean.
Yeah, you're right. You can say it like deprotonation or proton transfer.
Deprotonation.
Yes. So we did a proton transfer or deprotonation. That's the first step. Zoom in. Right, that's the first step to converting the OH into a better leaving group. So we took off this proton right here. Right, so this is pyridine. Pyridine is a base. It's actually a really good base and is used a lot in alcohol reactions because that OH proton has a pKa about 16 to 17. So you don't need a super strong base, but you need a good base to do proton transfer. So pyridine is a really good base. Right, so I'm gonna pull this off like that, boom, just like we did in part one. Right? So that will get me to here. All right, so now I have this pyridinium. Pyridinium ion, right? Normally, if an ion is negative, if it's positive, we end it in IUM, so pyridinium, and then if it's negative, we end it in ATE. Right, so Now, let's look at the next step. So what's the next step? What does it look like happening? Now, hold up, let me do something right quick. Move that negative out here. So what does it look like happen in the next step?
Is it substitution?
Well, it's not a substitution.
Oh, it bonded to the O.
Yes, you can see that the oxygen and sulfur did something together, right? Because you can see that SO bond right here. Is that right? But because sulfur has a pi bond, you can't do substitution, but you can do addition. So anytime you're reacting with a pi bond, you do an addition reaction. Pi bonds can't do substitution. They can do addition followed by elimination, and it'll look like a substitution, but they can't do direct substitution, right? So we're going to do an addition. Reaction. So the first step, when we did the proton transfer, that made oxygen a better nucleophile, right? It's not a leaving group yet, but it made it a better nucleophile for the next step, which is for it to attack the oxygen, the sulfur in the thionyl chloride molecule. So that proton transfer, let me put that in here. My finger is really sticking to this screen. So that step made oxygen a better nucleophile. And let me move that up. All right. So once it attacks, this is one of our intermediate. This is an intermediate that we get. All right. So now we need to look at the next step, which is the loss of chlorine. So this is again an addition followed by an elimination. Right. What's one of the key characteristics to know that you've done an elimination? Anybody? We learned this in part 1.
A leaving group?
That's one thing. Yes, I agree with you there. But there's one other. What's always formed in it after an elimination? What do we always get?
A double bond.
A pi bond. Good. So you can see right here, I got a pi bond here where this was. Can y'all see that?
Yes.
How would I do that? What arrows would I put in to show that formation? And I also lost the chlorine. So what arrows would I put in to show that elimination? And it doesn't matter which chlorine we take off.
One from the chlorine to the, oh, never mind.
You want to do that to put the pi bond in, is that right?
Yes.
And then the chlorine, let's take this one. Both of them have long pairs, by the way. I just don't have them drawn in. We'll do that. Right? We always want to, if chlorine, in this case, what is chlorine? It's my leaving group, isn't it?
Yes.
So if chlorine is my leaving group, always remember that the leaving group, when it leaves, it takes a pair of electrons with it. Right? It always takes electrons with it. So now chlorine over here is, I don't know, I have a negative sign on that. Negative. All right, are we okay?
Yes.
All right, so now if we look at the last, I'm gonna drag this over here. I just, this time I've been working with this. I should have fixed this a long time ago. I'm gonna wipe that out. Give me 1 second. Paste it wipe this arrow out too. All right, so now that same chlorine that got eliminated is going to become my nucleophile in the next step, which is the attack of chlorine on this thionyl compound right here at this CO bond, because I'm trying to replace oxygen, remember, so I need to substitute that. So it's a substitution. What type? If this is coming in at the same time and oxygen is leaving, and that process is happening simultaneously, what type of substitution is that?
Concerted.
It's concerted, that's right. It's a SN2, which falls under the category of a SN2 type substitution. All right, so I got that plus, and let me show you the end, this. Plus, I'll just copy this one over here. That, I'll put it up here. Cool. So all three of these things together. Right, but this is my main product. This is what I want. I wanted to replace oxygen. So I converted the alcohol into an alkyl halide using thionyl chloride. Now here's the question, or a question, not the question. This is all side product stuff. What do you think is going to happen between these two? You got a negatively charged oxygen. You got a positively charged nitrogen with a proton to give away. What do you think is going to happen?
Are they gonna bind together?
Or
A proton transfer?
a proton transfer to make everything back neutral. So I'm going to put that in here. So that's you're gonna do a proton transfer in that case, make everything neutral. And then if there's more alcohol, the pyridine is gonna go back in, do the same thing again, start the whole process over again. If there's more alcohol, if more thionyl chloride left, you'll go right back in and do the same process. All right, questions about the thionyl chloride reaction? All right, again, the reason why we have three different methods is because we might want to convert an alcohol into a chloride. We might want to convert it to a bromide, or we might want to convert a primary, and we need a method that'll work on a primary, even though we have methods that work on secondary and tertiary. So you can imagine with this being SN2, this thionyl chloride reaction, since it's SN2, it's going to work better on a primary alcohol than it would a secondary or tertiary. Tertiary won't work at all. You have to use a different method. All right. Any questions about this at all? All right, let's go down and work some of these problems. But I think we have enough information to start hitting these and talking about them. So let's look at A. This is just simply giving the right reagents. We're not going through any mechanism or anything. All right, We're going to talk about the mechanism, but we're not going to put the arrows in because we've already seen that. All right, so the first question, it says give the correct reagents to convert given star materials into the products shown. So look at this first alcohol. We're going to do all of these. What would you do with that? How would you take that OH off and stick a bromine in its place?
Proton transfer.
Okay, that's part of the process, but what
about NBS?
Now, NBS, not in this case. NBS is for allylic bromination, or you can use it for halohydrin, but in this case, we got 3 options. We can do, I'm gonna write them up here as a cheat sheet. We can do HX, where X is a halogen. We can do thionyl chloride. Or we can do PBr3. And remember, each one of these methods works best on a specific type of alcohol, right? This is primary, secondary, right? This is primary. And then over here, this is tertiary. So it's just like, it's like, how do I want to put this? Never mind, I'm not gonna use that analogy. You pick your reagents based on your start materials, right? So if you're looking at first example, what type of alcohol am I starting with? Is it primary? Is it secondary? Is it tertiary?
Tertiary.
It's tertiary, right? This is a tertiary alcohol. Anybody not see how it's tertiary? It's got 3 groups attached to the carbon where the alcohol is, right? This is the carbonyl carbon, and it's got 3 groups around it, so it's tertiary. So of those methods, which one are you going to pick? Are you going to pick thionyl chloride?
No.
No, because it's specific for primaries. PBr3 is primary, secondary. So you need to use HX, but what do we need X to be in order to turn that OH into a bromine?
A halogen.
Yeah, which halogen?
Bromine.
Bromine.
Good. So we need this to be HBr. That's going to help us. None of the other reagents are going to help us. So we got 3 sets of reagents that we can use. We're going to pick the one that's most suitable for tertiary alcohols in this case. All right. Now it says determine the type of substitution method or mechanism, type of substitution mechanism. So it's SN1, SN2. What do we know about this reaction based on the mechanism? How does it work? What's the first thing that happens? Anybody?
The proton transfer.
Proton transfer followed by what? That's good. You're right. And then what happens after proton transfer?
Then it creates that leaving group, a better leaving.
Yep.
And then,
keep going. If you make something into a leaving group, what does it have to do?
So then you have to go through, then it's an actual substitution, right?
Yeah, but you said it. You make OH into a leaving group by doing proton transfer. Mm-hmm. And then what happens after that? If you turn it into a leaving group, what does it have to do?
Leave.
It got to leave. So when it leaves, you make a carbocation intermediate, right? So carbon ends up positive. So we'll end up with the intermediate in this case that looks like this, with a plus charge on carbon. Is that right? So we'll end up with this. Russell. Which eventually gets substituted with bromine, right? So this is, if it goes through a carbocation intermediate, it's not concerted, right? So this is going to be an SN1 type substitution. Are y'all following that?
Yes.
Yeah.
It happens in steps instead of all together.
Right.
Yeah.
Right. So down here, let's look at the next one. There's a couple of things we're gonna talk about on this problem. Go ahead. I have something in the chat. All right. First of all, what type of alcohol is that? Is it primary? Is it secondary? Is it tertiary?
Secondary.
Secondary. So remember I said up here, HX is, best suited for tertiary. Thionyl chloride, best suited for primary, but it can work on a secondary. And then PBR, I didn't even put the 3 in, sorry. PBR3 is best suited for primary and secondary also. So I'm gonna put in parentheses up here. If I can write. That it can work on a secondary. That's a little slower, but it can work. So if I want to turn OH into a chlorine, which method am I going to pick?
The PBR3.
I want it to be a chlorine, though. If I use PBR3, it's going to turn into a bromine.
So
right?
you would, yeah, so then you would have to use the second
Thionyl.
the thionyl.
I want to use thionyl chloride. All right, here's another piece of information. Because I don't remember if we got this deep with it in part 1, but I want you to notice something. Look at the OH. What's the configuration here? Let's go all the way back to that. Uh-oh, wrong pen. What's the configuration on that stereo center? Can we tell that from here? I think we can. That's going to be 1. That's going to be 2. That's going to be 3. Is that right? And H is already back. Is that right?
Yeah, so it would be S.
It's S. Good. Excellent. Then over here, notice it's on a dash line. I don't know why they drew it upside down like that. I didn't make this problem, but it's on a dash, right? But the configuration switches. Do you see that? Oh, my art is horrible.
It switches because now H is on a wedge type thing.
Mm-hmm. Can you see that? That chlorine is going back. Yeah. You see how it changes? That's a clue to the next question. What type of substitution? Well, we already know that with thionyl chloride, what did we say? Did we say the substitution step was stepwise or concerted?
Concerted.
It's concerted. So we already know that it's SN2. But now we see another consequence of the SN2 mechanism, which is that you get what we call inversion of stereochemistry. That's how you can always tell if a reaction goes to an SN2 mechanism is if it happens at a chiral center, it's going to get inverted. I'm going to show you why. Right, you get inversion of stereochemistry. What happens is, remember we said it's concerted, right? So what happens is, so here's my carbon, here's my leaving group, and then here are the groups around the carbon. I'm just gonna I'm just gonna abbreviate. I'm not gonna draw the whole structure, right? But those are the groups around the carbon. All right. And so when the nucleophile comes in, it's got to come from the backside and cause the leaving group to leave. Right. That's how it gets in. And that's the whole purpose Oh, that's the whole reasoning behind that inversion that you see, because clearly it's S in the star material, but the product is R. And the reason for that is because it's concerted, the nucleophile is going to attack from the opposite side of where the leaving group is. Now, don't get this confused with pre-existing stereo centers. It's a different. This is a different idea. All right, the pre-existing stereo, but it's the same reasoning, and it's sterics, right? The nucleophile doesn't want to come in from the same side where the leaving group is because it just can't get in that space. So it's going to come from the opposite side. Does that make sense? Like, why would it come here and bump into the leaving group and increase the energy? Like, that's not going to happen. Right? That won't happen. The nucleophile coming from the same side, no way. Out of the question. Because if it does, it's going to encounter the leaving group. You're going to get all kind of steric interference, and it's going to raise the energy of that reaction to the point where it won't happen, right? So you want to follow the lowest energy pathway. All right, questions about that?
Yes, so like, I hope this isn't a dumb question, but like,
No.
how do you realize when it's SN2 and SN1? Because I'm still struggling to comprehend.
So, okay, so let me answer that in two parts. So first, but we went through the mechanisms for each one of the reactions, and we gave that information when we got to the substitution step, whether it's concerted or whether it's stepwise. That's one way. The second way is that if you were to go through the mechanism on your own, when you get to the step where it's time to do the substitution, if the leaving group leaves first and leaves a carbocation behind, then you know it's SN1. If the leaving group is there and the incoming nucleophile is pushing it out at the same time, then you know it's SN2. The third way is to look at something like this, where you see a change in stereochemistry at that reactive site. So how it started out S and ended up R, that's a dead giveaway. That is SN2, because that's a key characteristic of that mechanism, that is inverts.
Okay, understood. Thank you.
Right, that's actually a really good question. Somebody else had it but was scared to ask it. So thank you for your bravery. All right. Look at the next question and tell me what you would use, and tell me what the reagents would be. So what the reagents are, and what the mechanism is, the substitution mechanism. Is it SN2 or SN1? Let me see if you're paying attention. I can zoom in on it too so you can see the stereochemistry and all that. So what would you use, first of all, to take OH and turn it into bromine?
PBr3.
Excellent. You are paying attention. So PBr3 is going to be my set of reagents. Let me fix my 3. All right. Now, is the mechanism, the substitution part, SN1 or SN2?
SN2.
Great. How do you know?
Because of the inversion. Because of the inversion.
Because we see the same thing happening here. I need a different color highlighter because that's not good. We see the same thing happening here that we saw in the top reaction. Is that right? The OH is on a dash on the other side. And then over here, it's on a wedge. Is that right?
Yeah, that's correct.
Okay. Now let me ask this question, because this does have a pre-existing stereocenter, right? Look at where bromine is You see how it's, of course, it's wedged, but look at the stereochemistry of the other substituent down here. Right? You notice how bromine is opposite to that too?
Yes.
Yeah. So it goes all the way back to what we were talking about with pre-existing stereosynthesis. So this is going to be the major product, and you may have 1.1% of another product where bromine is added to the other side, but it won't be competitive, right? This product is going to predominate. All right. So you see how all these other concepts kind of tie in. That's why it's important to get the foundational stuff. So when we see stuff other than what we're studying, stuff that we've already studied, we can identify it and discuss it. All right, what about D? What would you do with D?
That's a primary alcohol.
Great. It's a primary. So what method would you use?
But you want that chloride in it, so you can use the the thiol.
Yes. Yes. We don't worry about stereochemistry, none of that stuff, because it's not chiral. All right. What about the next one? What would you do? You got a tertiary, another tertiary, and you want that OH to be converted into a bromine. What would you use?
The HX.
Yep. And X is going to be bromine in this case.
Bromine,
right?
Yeah, hydrobromine.
So this is SN2, and this will be what? SN what?
1.
SN1, right? We know it's SN1 because it's, and this answer, I can't see who asked that last question about how do we know, but when we talk about substitution and elimination in more depth, there's some checks that you can do at the very beginning to know whether it's going to be SN1 or SN2. And one of those checks is to look at the structure of your substrate. So if that alcohol on the very bottom is tertiary, it's automatic that it's going to go through a SN1 mechanism because it's too crowded to go through a SN2. The nucleophile can't get in from that backside. So the leaving group has to leave first. So SN1 is automatic for that. The primary SN2 is automatic because the carbocation that you would get if the leaving group left first would be too unstable. So that's one of the main ways to be able to distinguish between those types of substitution is to look at what you start with. If it's primary, it's SN2 always. If it's secondary, it can go either way. And if it's tertiary, then it's only SN1. So let me write that down somewhere up in here. Come on, finger. All right, so if it's a primary substrate, and that's just a fancy word for starting material. That's what whatever reagent my leaving group is on, that's the substrate. So if it's primary, it's only SN2. If it's secondary, a secondary substrate, it can do either one. It depends on some other conditions like the solvent and stuff like that. And if it's tertiary, if it's a tertiary substrate, then it's only SN1. So even if you don't know the mechanism, if you don't know the arrows, if you don't know any of that stuff, you can look at the structure. If you know what primary, secondary, and tertiary looks like, you'll be able to say definitively that it's SN1 or SN2 if you know how to identify a structure. All right, does that help at all? I think that's the easiest way to go about it. And then there's some other more nuanced ways, like looking at the solvent, looking at the stereochemistry and things like that.
No, that helped. It was Brianna Peoples that had that question.
Okay, great. I'm glad that helped. All right. It says also to draw a reaction energy diagram for A and C. How many of you remember what the energy diagram looks like? Anybody? I'm gonna draw it right over on the side. What does it tell us?
Is it that roller coaster? It looks kind of like a roller coaster, right?
Who is that?
In time, Carlin.
I like that. I like that description. It does look like a roller coaster. And on the x-axis,
you have time, and on the axis, you have energy.
Yep. Man, I like that. That's a great answer for roller coaster. Now, what's gonna? I'm gonna stick with that. I'm gonna use that too. Hope you don't mind.
You got it.
You know, it's 2021. We still memes, and we screenshot stuff and pretend like we said it. So I'm gonna use that again.
Okay.
I'm still in that one, with your permission. So time, right? Or we call this the reaction coordinate. And then on the y-axis, and that's I'm impressed by that. I might buy you lunch today. I think you just earned it.
Oh, for real?
Yeah, because that I've never heard it described like that, but it's a perfect description. It does look like a roller coaster. Now here's the question: how many times does that roller coaster go up and down? What determines that?
The intermediate.
Okay, great. So the number of intermediates or the number of steps. Is that right?
Yeah. So
if we go to this reaction, I'm just going to write the steps down. Right? We know, because this is A, we know the first step is what? Proton transfer. Get your words right, Russell. Proton transfer, is that right? Second step, which is the rate determining step, loss of leaving group. And then the third step is nucleophilic attack. I'm not going back through the arrows because you can flip back in your notes and see that. Is that right? That's what happens. Proton transfer to make the OH a beta leaving group. Then because it's a beta leaving group, it leaves spontaneously because this is a tertiary carbon. It's an SN1 mechanism. And then because the carbocation is formed, the nucleophile attacks it, right? So over here, how many times would that roller coaster, how many humps would that roller coaster have? Because every hump corresponds to a step. Is that right?
Yeah, so it would have 3 total.
It would have 3 humps. Good. You see it? Man, I'm telling you, that was a brilliant description. Definitely put your cash out in the chat. All right. So first step, proton transfer is really quick, exothermic. Really fast. So it's going to have a low activation energy. Boom. Take us down to that intermediate hydronium, right? Is that right? When it does proton transfer, don't you get while I draw it in, you'll get this. I got to zoom way in on that. Is that right?
Yes. Yeah.
I'm just going to put star materials right here. So the intermediate hydronium is going to show up here. Is that up or down? It's down. It's close enough. Let me fix that so it'll look neater. And it made it look worse. All right. Sorry. So this is the hydronium intermediate from the first step. And then the second step we said was the loss of leaving group, which we talked about Monday. And we said that that was the rate determining step. What does that mean in terms of activation energy when you compare it to all the other steps in the mechanism? Does it have a higher activation energy?
Yes.
Yeah. So we're going to draw that like this. Sorry. We're going to draw that like this. See the activation energy difference. Come on, Russell. Draw it like that. And then it'll have a activation energy difference. Here, you can see the difference, right? Big difference. And let me put that in there. That's my first time using that dotted line pen, by the way. This would be delta G double dagger. Same thing over here. All right. And I'll make that look better before I upload this. All right, and then we got a third step, which is going to be what? And this is going to give you this intermediate.
Dr. Russell,
Go ahead.
one of my classmates before he even drew the graph was like, it's gonna have 3 humps. And what was the telltale sign for that?
Say that again. Oh, the fact that you know how many steps take place in the mechanism. Like when we went through the mechanism, you know, you had the proton transfer, then you had the loss of leaving group, and then the final step was attack of the nucleophile. So that's how we know, if we know the mechanism, even if you don't know the arrows, if you know the parts of the mechanism, you can know what the reaction energy diagram will look like.
So that means that, like, for example, the loss of the leaving group, it would always have the highest hump type thing.
Yes. If it's SN1, the rate determining step is always loss of leaving group. Yep. Great question. Yeah, the rate determining step is going to control the rate of the reaction, the overall rate. And then the last step was just nucleophilic attack. So we're going to throw that in right here. That's going to be pretty fast. So it's going to have low activation energy. And then this is going to be my product, which I'm going to abbreviate as, if you ever see me write PDT, that's an abbreviation for product. Okay. And that's also going to have a low, that's a fast reaction compared to the loss of leaving group. We're okay with that? So over here, that's going to give me this. Right, that's my product. I'm gonna replace this. All right. And so that reaction energy diagram is gonna have 3 humps to it, just like that. It's gonna have, and every well is an intermediate, and every peak is a what? Anybody?
Transition state. I mean, not the state.
Yeah, you're right. Transition state. Every peak is a transition state. Every well is an intermediate. All right. So let's go to, did this say A and C? Yeah, let's go to C. C is concerted, isn't it?
Yes.
Mm-hmm. And then there are only, remember from this, for this reaction, it only had so attack of OH on PBr3, that was a step. And then the second step was nucleophilic attack for bromine. All right. We only have to go through that mechanism. It's only 2 steps. So what would the diagram look like? The roller coaster.
2 humps.
2 humps. Which one is going to have the highest activation energy? So see, for SN2, the rate determining step is the substitution, right? It's not the loss of leaving group, because that's happening at the same time that the nucleophile is coming in. So I got one little step here where the OH attacks PBr3 to give me that intermediate. So that'll look like this. I have room to draw it. Put the stereochemistry. All right. And then after that is the attack of bromine, Br minus. So I'm gonna write that. So that's gonna be rate determinant. So I can make that have a little bit higher activation energy than the first step, right? So that's gonna give me my product. Right? So that's the energy diagram for that. It's 2 steps. First step is the attack of OH on PBr3. Second step is the attack of Br on that intermediate. Oh, let me make sure that's accurate. It's got a positive charge on oxygen. All right. Questions about either one of those things? So this is a good problem to look at in reference to these reactions, because it ties a lot of stuff in together, right? It ties in the mechanism, it ties in the energy diagram part of the mechanism. It also ties in knowing what reagents to use with what types of alcohols, and the substitution part, like whether it's SN2 or SN1. I think that's the last question on that page. And we only got 0 minutes left. Let's do this last one first, and then I'm going to assign this as on your own here. And then here, we're going to probably we'll talk about this Friday before we move on to another topic. But I want you to do this one on your own. All right? But let's do this top one. How do we know which one of these? How do we know the stability of a cation? I think we talked about that. And it says in order of decrease in stability. So least stable. I'm sorry, most stable to least stable. Well, 1 is most stable. Which one is the most stable out of the 4?
Probably the one. Oh, no.
Go ahead.
I was going to say the CH3.
So that's tertiary, that's secondary, that's primary, and this is what we call a methyl. Carbocation wise, the CH3 is actually the worst of all of them. Mm. Remember when we talked about this on Monday, we talked about like how carbocations are stabilized. Anybody remember the term we used? Hyperconjugation.
More substituents, the more stable it would be.
Yeah, the more substituents you have, the more stable it is, because those substituents donate electron density to the plus charge. Is that right?
Yes.
Mm-hmm. So you don't have any substituents here. So that's the worst. So this is going to be 4. And then right after that, the primary only has 1 substituent. So this is going to be 3. And by default, that's 2. And this is 1, because you can see it's tertiary, right? It's got 3 different things attached to the carbocation. So, and all of those have a dipole going towards the carbocation. So they're giving it electron density, not electrons. I think I wrote it backwards, but I think it said 1 is the most stable. Put 3. It should be 1. Yeah. All right. We're gonna stop here. We'll pick this up Friday, finish it out, and then we're gonna start the application part, because we've already talked about how to make alkyl halides. So on Friday, we're gonna talk about how to use them. One of the ways to use it. All right. Who was that gave me the roller coaster analogy?
Harlan Logwood.
Logwood. I need your cash out because I'm buying you lunch today.
Okay. I sent it to you in the chat.
Oh, I see it. Yep. I'm about to go ahead and do that now before I forget.
Thank you.
Yep. Nice work. thank you for that analogy. That was really good.
And you have my permission to take it.
Oh, don't worry, I'm still in there. Yeah. All right, y'all have a great day, and I'll see y'all on Friday. Remember, the test is going to be posted. I didn't get a chance to set the time on it, like not the time, but to set a time for it to like become available. So I'm just gonna post it after my next class, but it'll be posted by noon, and then you'll have until Friday at 11:59 to finish
it. Okay, thank you.
All right, y'all have any questions? Just shoot me an email.
Thank you. Have a good day.
All right, y'all take care.